This is the fuel efficiency of the Prius problem. So there was this poll on the internet, and 14 users took it, and they all drove 2012 Toyota Priuses. And the mean fuel economy that they got is 53.3 miles per gallon, and the standard deviation was 5.2 miles per gallon. So this is the standard deviation of our sample, and this is our sample mean. I've got this over here. Standard deviation of the sample we call S. Sample mean we call X bar, which we already know, right? It says in part A, the EPA claims that the 2012 Prius gets 50 miles per gallon. Do these data provide strong evidence against this estimate for drivers who participate in this poll? So we are going to choose this one. The mean for all drivers is 50, and we just want to know, is it possible that the mean is not actually 50? It's different. So we're going to pick this. Our sample size is 14. The degrees of freedom are always 1 less than 14. And we will come up with our test statistic in just a minute, but I want to take a second look at our textbook and see what, come back to this table, and see what is wrong. So this is the reading, this is 7.1. Our mean is 50, right? And our standard deviation is sigma over the square root of n. Standard error is sigma over the square root of n. It says, when we collect a sufficiently large sample of n independent observations from a population with mean mu and standard deviation sigma, the sampling distribution of x bar will be nearly normal. Well, there's some problems, right? We want to be able to use the central limit theorem for this, just like we were doing it with a proportion, except for we don't know this. We don't know what sigma is. We just know what s is. So we don't know the standard deviation for every single Prius owner. We just know it for these 14 Prius owners. That's a really small sample size. If we, the first part of this, it says, when we collect a sufficiently large sample of n, well, we don't have a sufficiently large sample of n. We have 14 people. So we can't use a normal distribution here. So what we do is scroll down. And what we're going to do instead is we're going to use the t-distribution. And the t-distribution gets around it having a large sample by just saying, well, just take your sample standard deviation, S, when you're computing your standard error. And when you have a small sample size, we're going to just change our distribution every single time. Cool. And that'll be dictated by the degrees of freedom, which is always 1 less than what your sample is. All right. Let's see. 414. Alrighty. I don't know if it tells us what alpha is in this problem. Let's go ahead and say alphas equals 0.05. That's what we usually say it is anyway, right? We just decided this was a two-tailed test, though, right? So we got to keep that in mind when we are doing these things. So here's our test statistic. We compute it just like we compute a z-score, and we were doing in the previous section for proportions, right? So I'll type this out in the comments section. We take our sample mean, which is 53.3. We subtract the population mean, which is mu, or 50. And we divide by our standard error. Remember, our standard error for this type of problem is going to be our sample standard deviation divided by the square root of our population size. So this is our test statistic. We can get our p-value from the test statistic just by typing in t-distribution. Well, this is a t-distribution, right? I'll type in t.dist distribution. The x value is my test statistic. My degrees of freedom, I just found out, is 13. So I'm going to do comma 13. And I want this to be true. Boop. It says my p-value is 0.983. But this is the value, this is the left-hand side of this test statistic, right? And right now we're looking at the right-hand side of it. So we should do 1 minus this value. And because it is for two tails, we should double it, right? We were saying that the null hypothesis and the alternative hypothesis is that mu and the sample mean are different. So we're just going to double this value to get this. We can also think about this in another way by using this table over here. These are all spitting out critical values for different alphas that we've got, right? So this is a two-tailed test that we're doing, so we're only focused on this bottom part. we said we want our alpha to be 0.5, so we're only focused on this column here, right? And so we want to find the intersection of 13 degrees of freedom and the alpha of 0.5. So that's this number right here, 2.16. So this is the critical number for this problem. Assuming this is the right alpha. If our alpha is different, we'd have to change it. But our critical number is 2.16. And so then we can say, well, look at our test statistic is way bigger than the critical number. So we are going to reject the null hypothesis. Yeah, we can also say, well, this number is smaller than our alpha value, so that would also reject the null hypothesis. It's however you want to think about it. Once again, I'll put the formula for our test statistic up in the notes, not in the notes, in the comments. And if you have any other comments, feel free to post.